Welcome to another episode of Don't Panic Geocacher. My name is Arjen and I go by the name Waterfan5 on the geocaching.com website. In today's episode, we're going to talk about base conversions, and the title is all about that base. If you don't know what base conversions are, don't worry, I'm going to explain it, what base conversions are and how they're used in geocaching puzzles. If you already know what they are, I still recommend that you listen because I'm going to show you several tips and tricks of how to recognize base conversions, some helpful tools, going to solve some puzzles with base conversions, and also how base conversions can trick you when using puzzles. Base conversions are a very often used technique in puzzles and therefore is a must-have for every geocacher that wants to do puzzles that they can understand, maybe even convert manually from one system to another base system and do a base conversion. Very essential skill. So with that, let's get started. Base conversions are required when a number is using a different system to represent when multiple digits in a number are used. So this means that some math will be involved in these puzzles, but I'll try to keep it simple, and especially when we start using tools, you no longer need to know the math, you just need to know the tips and tricks. But for those of you that want to know the background, I'm going to give quite a detailed background on how to do the base conversions, both manually as well as automated, as it will help you recognize base conversions in puzzles and how important they are. So we live in a base 10 world, probably inspired by the fact that we have 10 fingers, and that means that every number that we use always goes to a multiply of 10. So we start with 1, then 10 times 1 is 10, 10 times 10 is 100, and so on, 1000, 10,000, 100,000, etc. So that means that we also have 10 numbers, right, that we start with, from 0 to 9. That is basically our base numbers that we use. So that means that if you see a number, like the number that I show here below, 70,132, that means basically if you would take that apart, it means 2 times 1 plus 3 times 10 plus 1 times 100 plus 0 times 1,000 plus 7 times 10,000, giving you a total of that number, right? 70,132. And that is because we live in a base 10 world. Now, let's pretend that the world is slightly different and we only have 5 numbers, so from 0 to 4. So if we have from 0 to 4, means that everything is going to be a multiply of 5. So instead of using the numbers 1 to 10, we're now using in a base 5, and the first one is 5. The next number would be multiplied by 5 instead of by 10 as it is in the base 10 world. And the next one would be multiplied by 25, 125, and 625 in our base 10 system, right? In the base 5 system, the number 5 doesn't even exist. It is just for our understanding because we live in the base 10 world. So that means that we have a number 40132, which now say it's a base 5 number. We should interpret that in our base 10 system as follows. 2 times 1 is 2, 3 times 5 is 15, 1 times 25 is 25, 0 times 125, and 4 times 625 is 2500. We add all those numbers together, and in base 10, this would be 2542. So, as I mentioned, in base 5, the number 5 doesn't even exist. We only use numbers 0 to 4, but in base 10, of course, we have 0 to 9. If you use less numbers, it means your number will get longer, and we see that often already here. In base 5, to represent this number, right, this volume, this arbitrary volume, we needed 5 digits. In the base 10, we can represent the same volume, the same amount of numbers, with only 4 digits. But in reality, if we think about it, it represents the same number. It's still, let's say, a bucket full of balls. In one case, it was 2542, and if we mention it, it say, oh, it's 2542. But in a base 5 world, that would be 40,132, even though we're talking about exactly the same volume. And this is important to understand. The same number, the same amount, whatever that amount is represented in different bases by a different number. And this makes it ideal for geocaching puzzles. We work with numbers, we represent numbers. However, by now doing a base conversion, you can make a number look completely different, even though it represents the same volume, the same number of degrees, the same number of minutes, the same number of everything. We can now make it look different, and of course, that now makes it a puzzle. You may be familiar with the word binary. And binary is just one of the more common base conversions. Because what it does is it uses a binary system, with only zeros and ones in this case, to represent a number. And so that means that the multiplication table now is every time it is times 2. So we get 1, 2, 4, 8, 16, and then the next one will be 32, and so on. And any number can now only use zeros and ones. I talk about this in a video where I talk about binary systems as well. This is of course only one example of binary systems. There's many other ones, but for base conversions, this is the interpretation that we would use. So if we now have a number like this, we now interpret it by doing the multiplications, similar like we did before. Start at the right and go to the left, right? 1 times 1, 0 times 2, 1 times 4, 0 times 8, 1 times 16. And we just add the ones together and we get 21 in the base 10 system. Again, we see that the number got a lot longer, used more digits. So 10101 is now 21 in base 10. Now, other popular one is base 8, because also it's a multiple of 2. And now, of course, we use 8, 64, 512, 4096. But now let's take a look at that same number that we saw before, right, in base 10. Now, this is a perfectly valid number in base 8 because we use from 0 to 7, so this is a number. However, it no longer means the same amount that we think it does if it is in a base 8 system. Because if we start doing the calculation, 2 times 1, 3 times 8, 1 times 64, 0 times 512, and so on, we add those numbers together. For us in a base 10 system, this means 28,000. While in the base 8 system, it would be that same volume amount would be represented by 70,132. So, and actually I'm more correct, 70132. It's no longer the word thousand. Doesn't necessarily represent the same thing anymore. So this is important to realize that the same number is no longer the same volume because of a different base system. This may be easier represented if we truly concentrate on that volume. So let's take a look at a more generic example. The picture that you see here is the National Stadium in Brazil. And you see it fits a lot of people. Roughly about 70,000 people fit in the Stadium of Brazil. However, if I represent that in a different base system, then that would be a completely number representing that same 70,000. So the number of people don't change, it is just the way that I describe the number of people. Computer in binary somewhere would store this number with all zeros and ones in some shape or form. But the same base 7 system represents the same amount of people. So all these numbers represent the same amount of people. We just use base 10, but in base 5 it would be this, and in base 7 it would be this. So let's again take that as a reverse. So we use base 7, so we have to use multiplications of base 7, and we basically take the number apart. 6 times 1, 1 times 7, 3 times 49, 1 times 343, and so on. We add it together and we get now our base 10 number. So we see how we can convert from one base to back to base 10, right? still representing the same amount. And this is why it's so popular in geocaching puzzles. So let's take a look at an actual geocaching variant of this, right? So let's say that for whatever reason, because the cache was hidden there, is at the Statue of Liberty. Now you can look up at Google, you can find the location, or with your GPS you can measure the location, and this is one of the locations near the Statue of Liberty, of course in base 10. But all these other numbers that you see here, coordinates that you see here, still represent the Statue of Liberty, just not in base 10, but in base 9, base 8, base 7, whatever is used here. And what I did is for each one, I just took the number and represented it to the specific base. So, for example, in base 9, it would be 9 times 4 is 36, plus 4 is 40. Same here, 9 times 6 plus 5 is 41. And here, of course, it gets slightly more complicated because it would be 8 plus 2 times 9 plus 4 times 81 would result in 350. So all these represent the same coordinate, just in a different base system. And you can see several elements here that are very specific to base conversions. So the base 2 conversions is of course a lot longer. So you see that the higher the base, the numbers will get shorter. It's not always consistent, 2 can be the same length, but they will get shorter overall. Also, the number of different digits used, right? As base 2, binary, only uses zeros and ones. Base 3 uses 0, 1, and 2. And base 4 uses, of course, also 3s, and so on. The higher numbers, characters simply don't exist in that base system. So this is also a way to recognize them, right? So if you see a number that has a lot of low numbers in there, and it looks longer than you expect the coordinate to be, or expecting the number to be, a base conversion may come into play. Wait a minute, it says 130 and 131. Well, our degrees can't be 131. Maybe I don't see any 5s, I don't see any 6s, I don't see any 7s used. Maybe it is a base 5 system, right? That is how you can look at these puzzles and recognize that by having too many digits, that have digits that don't use the higher numbers, like 6, 7, 8, or anything, you know that it might now be a base conversion that comes into play. When computers became popular, initially it was all 8-bit computers. At some point that became 16-bit computers, and so hexadecimal became a very popular system for computers to use. And then in the 90s we got 32-bit systems, 64-bit systems later on, and so on. However, that is not the only system that of course you can use. Anything higher, of course, is being mentioned. And with different characters, as you can see here. So we see, for example, now again the Statue of Liberty represented in different base systems. Now you start seeing that they start using these letters. And again, the same type of conversion, right? So if I do base 11, it's 3 times 11 plus 7. So 33 plus 7 is 40. And so on. So this is a base 7 system. We don't really notice here it getting shorter much because we have 6 not so high numbers. So we'll get roughly the same volume. But you do see the main number getting lower and lower. 3, 2, 1, and eventually there will be a base system where we can just represent it with 1. And you can actually immediately think about which base system that would be, right? What base system could represent 40 as one number? Well, base 41, right? Because if you can represent 40 digits, this could be represented by one number. So bases can be as high as you want to go, as long as you have symbols to represent it, to represent the different entities in it, you can do a higher number. And so again, you may recognize this, right? Because you see some of the weirder characters. So when you now see this and you see the number being way lower, but the ratio roughly seems to match. So for example, here between 24 and 42 and 40 and 74, this number is higher. And so it's like, maybe some base conversion is going on. Not exactly for example, 18 difference and then again 18 difference. We don't see any standard math like that, but they seem to be comparable to each other in how they compare to each other. So they are, one is bigger by a certain amount, by a certain ratio. So that's something that you can take a look at when you see these numbers and you see this ratio, but there's not plain math involved, simple math involved. We may have to do with a base conversion. Of course, we may also see other characters being introduced. So now we're going to make your head spin, because we have the Statue of Liberty and we have this number. This is, of course, the base 10 GPS coordinate. But what if we say, well, what if this was not a base 10 number? What if this was a different base number? We saw before that if we converted this number to another base, how it would impact. What if we just say, you know what? This is written in another base. Not every base would work, right? Which one wouldn't work? Well, any one that would have a digit used in here that doesn't exist. Binary 0 and 1. This is not 0s and 1s. So this can't be a binary number. But anything higher than an 8, because we're using 0 to 7, would in this case be a valid number. So, for example, this number, if we converted that from base 11, so instead of to base 11, we go from base 11, we get that in base 10, it would look this, would represent in base 11 the Statue of Liberty coordinates that we recognize in base 10. So now we're doing basically another step to it. So for example, in base 20, this is a if this was a base 20 number, then in base 10 it would be represented like this. So 80 would mean that 4 times 20 is 8, and then 0. 4 times 20 plus 1 is 81. So this is a base 20 conversion, but now we're converting from instead of to. So we're converting in the opposite direction. So this number, although we, of course, think of this as a base 10, for a puzzle, it doesn't have to be. It just has to be the number that people have to enter in the coordinates. So we say, well, we want people to convert and to, we can give all these nice numbers. And we say, oh, that looks all nice numbers. But, of course, looks nowhere near the coordinates that we're looking for. It can be very complicated, right? You see all these different numbers. But if we need to know that we need to be in the 40-41 range, 80-81, looks suspiciously close. Of course, 1300 is way too big. But they use base conversions, right? So now we have to realize that we have to convert the other way around. This is a base 10 number, and we're converting to an unknown base. In this case, this unknown base being base 20. So this is something that you have to take into account, that source and the target can very easily be reversed. There's nothing that says that the final result needs to be base 10. The final result can be any of these other bases, as long as the numbers are known and we have enough numbers to represent it. We can do to that base from any other base. So this makes it slightly more complicated, because now we get, of course, all these nice numbers, and it looks very valid to us like a base 10 system, but we have to realize this is really not written in base 10. They just have taken all the other numbers out so that it looks like a base 10 number, but really it's a base 20 number or some other base number that the original coordinates were written in. And these are the base 10 numbers. So slightly more complicated. It takes some getting used to take a look at that, but it's just a matter of swapping source and the destination in the base. And now we want to make it completely complicated. We're saying, well, what if neither of them is base 10? So in other words, here we have the numbers that were given. We know it must be a higher than base 13 to go with it, right? Because we have the letter C in here. So it's higher than base 13, but any conversion doesn't give us the Statue of Liberty. because the Statue of Liberty was 4041, and we don't have that here. We have one that looks close, but it is not base 16 because it's not the Statue of Liberty, even though it gives us, of course, a perfectly valid number. But if we're looking for something in the 74 range, this is not correct. This is because neither the source nor the target were base 10. So what we would have to do is try all of these and now convert those to base 10 again and see if any of these in base 10 would look good again, or in any other base would look good again, because we know in base 10 that was not the solution. We converted all these to base 10. If you look at what the right solution is for this one was actually we had to convert to base 20. Base 20, it was this. We now represented that all of two other bases, and we now see in base 12 that it actually is the correct coordinate. So in other words, our original puzzle and 2829 in base 20 represents this number in base 12. Very complicated to solve these type of puzzles, but there is a variety of them out there where neither the source nor the target is based in. So that means that you either have to do two conversions or use a tool that can directly convert from one base to another base. Hopefully, if there's a puzzle like that exists, they kind of give you which bases to use. Otherwise, you have to start looking at the numbers and see which ones are valid scenarios, and it becomes a lot of trial and error. So definitely my head is spinning right now when looking at all of that, and I assume yours is doing the same. Don't worry about that. It takes some while, it takes some practice with base conversions to get more familiar and to trust yourself more with them. Of course, there is also some tools that can help you, and I will demonstrate some of those tools later on as well. But before that, let's summarize a little bit, right? I gave some tips and tricks of base conversions, and just wanted to make sure that you remember these. That might be just as important as understanding how to do the conversions. Well, first of all, when you see a puzzle and you see numbers that look like there might be a base conversion involved, look at the highest digits that are used. So already showed you with binary base 2 that you only get like zeros and ones, right? So only 2 digits. If we see, for example, a number like this, there's no 8 and 9. Now that may be because the coordinates in your area may not require an 8 or 9, or the geocache puzzle may not require it, but it could also indicate a base conversion. So similar here, when we see the characters and we see here the highest is C, we know that the base conversion needs to be 13 or higher. Note, it doesn't say anything about the target, right? So already talked about that base 10 doesn't need to be your target. It just needs to be a number that you recognize as a coordinate, or it could even be a word you recognized as a coordinate. The other thing you need to take into account is that the ratio between numbers. So if we have a longitude and a latitude, base conversions will always go into the same direction, meaning that if one number is higher than the other, if you do a base conversion of both of them, one will stay higher than the other. So we see that here with the Statue of Liberty example. If we converted that to another base, one will stay higher than the other. 104 and 202, 140 and 74. 40 was lower than 74, 104 is lower than 2. And that is the case in all these base conversions. It doesn't matter which ones we do. The same for the minutes. This one, we see that the minutes in this case is higher for the latitude compared to the longitude. And the same is true for all after the base conversions as well. So this is something that you can recognize and look out for. If you see 2 sets of numbers and you expect one to be the latitude, one to be the longitude, they need to be in the same as your destination where you're going to, right? Your core coordinate. So for example, you can compare it to the posted coordinates and see which one is bigger, because in the base conversions, the biggest one will always stay the biggest one. The smallest one will always stay the smallest one. The other thing is to look for hints, like, do I need to do a base conversion? So hints, of course, could be the term base, baseball, um, the basis, the base of the puzzle. Anything that has the word base in it in a description could be a hint. The same with words like hex. I mentioned hexadecimal before. Binary, mentioned before. Octal, 8. So all those things are hints that there might be a specific base conversion. So look for that in the text or the title or the hint or anything if those numbers are used to indicate you're doing a base conversion. And the last thing, as I shown, base conversions can be in two directions, meaning you can convert to a certain base or from a certain base. So if it says base 7, it might be that your number you're given is in base 7 and you need to convert to base 10 or something else. Or it means you have to convert to base 7 to get the answer that you're looking for. Always remember you can go in two directions. That's a little bit of a summary. I'll tell you a little bit more theory later on, but first let's look at some tools. So here is a website I haven't used too much before. It's the unitconversion.org website, and it has a very convenient number conversion table tool. The idea is that you can enter a single number in it. So for example, in decimal, I can add a number and it will show it in all the base conversions. And it will show binary, octal, and hexadecimal separate, but of course that is the same as base 2, base 8, and base 16. And we'll see that when we enter a number. So for example, if I enter here the number 40, then we see all the other conversions. And you see here that the binary and the base 2 are identical, similar with the hexadecimal and base 16. You can also nicely see that the numbers like get shorter in characters and get a relatively lower number. It's what we would expect. And the nice thing is that this website is very interactive. So if I keep typing, it will update everything automatically. So it gives you a little bit of a quick tool to do trial and error to see if something is correct and see if something gives the number before. It does only one number at a time, so if I try to do two numbers, it doesn't work. But so you have to do each number individually. Note that you don't have to start with decimal, so it can also say like, hey, I think the number is like base 14 number, so I can just type in something here, and then you see all the other ones update. So all of them are both input as well as output, so making it a very convenient tool for bidirectional conversions. But there is more. Because so far we've always used like standard digits, right? From 0 to 9, and then if we ran short, we started moving on with the alphabet letters. But what if we didn't use 0 to 1 and just used only letters? So basically saying A means 0, B means 1, where before we said A means 10 because 0 was 0, 1 was 1, right? So basically we're only going to use letters. Now in base 10, this would still look somewhat the same, because in base 10 it almost becomes like a substitution cipher, because we're going from a 10 to a 10 just with a different alphabet. So E, which is the 4, is here a 4, and you see both 4s become an E. And A is a 0 because, well, A is 0. So it's almost like a substitution. But the next example is in a base 26. And now we see a much more complicated scenario because, yeah, the B and the B still goes to the same. But here you see, for example, with 350, it's only represented by two numbers, the N and the M. And that is because it's base 26. We're using the full alphabet. So B1 is 1 times 26 plus O, which is the 14th letter in this alphabet, is add together is 40. So we get the 40 again. And the same the other way around. If we do N, it's 13th letter in this alphabet, times 26 plus M is 12. Combined is 350. So you see the 350, while NM is 350 in this scenario. So you have to take into account that the base conversion may actually not use the standard alphabet. And for example, it could be a binary system that looks very much like a Bacon cipher, as I explained in one of the other videos, but actually is just a binary number, as you see right here, where the B is just a 1 and the A is just a 0. And again, this converts back to the Statue of Liberty. So be careful with that, because if something is pure letters, but you think it's a base cipher, it may actually be a base cipher with a different alphabet. And so you have to watch out for that when doing the conversion, to make sure that you're not starting with 10, because words would often then have numbers in it. And if you only see letters, most likely an alphabet of only letters was used. Now, this may look unusual, but actually this is used quite a bit, not only in puzzles, but actually geocaching.com uses the same thing. So here you see an example of that. This is a GC number of a puzzle, and A1VRX, and the geocaching toolbox has a way to convert it to a geocaching ID. So you see, you get this number. Now, how does that work? It's actually a base conversion. It's a base conversion with a custom alphabet and a 31 character alphabet. So these 31 characters. So it's 0 to 9 and then A to Z. But some letters have been removed. I, L, O, S, and U have been removed to avoid confusion. So O too much like a 0, I and L too much like a 1, S too much like a 5, and U too much like a V. So you get a 31, and they use the base 31 conversion. Meaning that if we take this number, so X times, it is the 28th letter in this alphabet, because we only have base 31, so we only have, this is from 0 to 31, 31, so this is 28. R is 4 down, so 24, but of course now times the 31. And then V, 2 further, 26, times 31 times 31, right, is 961, is this number, and so on. If we do that, we get this number. You have to subtract this magic number. They skipped all those. They didn't really start at 0. They started at this number. And so if you do that, we get this number minus this number is this number, which is our geocaching ID. This works for any geocaching ID that is 5 characters long. They use this base 31 conversion. For ones below that, they use a different mechanism. But once they started to the 5-digit system, this is the way you convert back. Fortunately, again, there's tools to help you do these type of conversions with alphabets. And I will show you one of them. Now, what if we go and use bases that are higher than 10? We use more than 10. Well, first of all, we're going to run out of symbols, right? We have only 0 to 9, and so we have to invent more symbols. And so, typical convention is that alphabet is being used. This is not mandatory, however. You can come up with any other system in a puzzle, and so a cache owner may have used a very different technique. Actually, we see in history some cultures have used different techniques. We'll get to that later on. But if we use just A, B, C as the next number, that means in our understanding, A would now mean 10, B would now be 11, C would now be 12, right? So on. And depending, the higher the base number is, the more we have to borrow. At some point we entered Z, and then we'll have to think about what is next to do, right? We have to start using other characters if we go with a base system that is higher than, well, 10 plus 26 letters, 36. So in base 37, we'll have to start inventing other symbols to use. Maybe exclamation points and other characters. So there's actually a very well-known system which is called hexadecimal that uses 16. And so you may see this keyword hex being used in puzzles. That may be a reference that is hexadecimal, a base 16 system is used. So now every digit can represent anywhere from 0 to 15. 0, of course, being the normal 0, 9 being the normal 9, but then A is 10, all the way to F being 15. So that means, for example, we can see a number that looks like this, 90AF2. And now we'll have to use these conversions that we did above, right? So we have, again, multiplications of 16. So those are the multiplication factors. But now we need to realize that if it's, for example, an F, that it really means 15. And A means 10. So we get 2 times 1 is 2. 15 times 16, 10 times 256, etc., and we add those numbers. So now we see exactly the opposite happening. Where with bases below 10 we saw it getting shorter, of course with bases above 10 we see that less characters can be used to represent a higher number. So base 16, of course, only used 5 characters to represent what in base 10 would be a 6-digit number. Again, it represents the same volume, the same amount, but it's just represented as a different string or number. So I'm going to use the geocaching.com toolbox, the geocachingtoolbox.com, to do some of the things I just talked about. So first the base conversions and the GC code conversions. So if I open this one and I use the GC code, it will convert it to the GC ID. And as I mentioned earlier, this is a special base 31 conversion. So we can use also the base conversion to get the same result, but we have to do slightly more steps. So if we go back, we open the base conversion. We mentioned it was a base 31 conversion, so the source was base 31 and the target was base 10. But not just any base 1, it had its own little alphabet. That was the alphabet without the 5 characters. So see that right here, I removed the I, the S, the other 5. And this was a base 1, but of course without the GC part, right? The standard. And we get here a number, and this is the number of which we have to subtract the 41120, and now we get that 8879,639 back. And so you see that it was the number that we had generated earlier. So very powerful tool with the base conversions, because we can do these base conversions with custom alphabets. I mentioned with standard letters, so for example with base 26, you see here that it uses 0 to 9 first. But that is not what we might want. We may want actually a regular alphabet where it just goes on like this, right? So the regular alphabet. Okay, and so now when I type in a word, hello, then basically, hello, then it would convert it to a number using a base 26 conversion, or the other way around. If I wanted to reverse them, I go base 10, I say this one is a base 26, and it would show, oh, that's this number. But if I wanted letters only, I again go to manual and switch it out, URST, and basically corresponds to this letter code, this number. So yeah, base conversions, not always with the standard alphabet, not always with the standard digits, so be aware of that there can be other ones out there. All this may look very far-fetched, right? With custom alphabets, different base rotations, but actually one of the old numeric systems, the Maya number systems, actually used all of that. It of course didn't use the Latin letters as we use, and they also didn't use a base 10 system. They used a base 20 system. So when you see an example of here where we see the numbers, well, their alphabet only had 3 characters. The dot, that meant 1, a dash, 5, and a shell, that meant 0. So in this case we have 2 dots, so 2 times 20 plus 0 times 1 is 40. 2 dots plus 1 times 1 is 41. So 2 plus 3 is 17 times 20 plus 2 times 5 times 1 is 340 plus 310 is 350, and so on. So this became a complete numeric system where each one was individually represented, and it was still a base conversion where it was a combination of characters. And of course at the end you can map out a coordinate again, and this is again the Statue of Liberty, but now in a Maya numeric system, which is a base 20 system. Very hard to read that this would be actually a base 20 unless you're familiar with the Mayan system, but it can all be decoded, as you can see, in the same mechanism that we used before. So next, I will show how to solve one of my own puzzles, chimpanzees coded abstract cybertext, the GC code that I just used before to convert to the ID, and not a field puzzle for difficulty. Yeah, it's pretty difficult, right, to solve this. And of course, there's some flavor text, and then the actual puzzle. This cache is hidden at the following coordinate, and it gives here a text. In other videos, I've shown this, and I will show this again. I often look first for hints. So I'll take the text, use a tool, one of my tools, the highlighter, paste the text in there, and say, okay, highlight some of keywords that we may find, right? So we have the numbers, but here we see, for example, the word base, play, because it might be playfair, sum up also is mentioned here. I discovered many variants, too many to sum up here. Okay, what base algorithm? The word base wasn't really necessary here. So all of those hint to that there might be clues there, right? It's always like, what do you focus on? Just in case you missed it, in the description, in the hint, it tells base of tree again. So again, it has the word base right here. So you should feel pretty good right now that base conversions might be the key. If you listen to the video, you know, of course, that if something has only letters, base 26 is a good candidate, base 36 is a good candidate. So let's take a look at that and go to, for example, Decode, just as a website, and we'll do the encoder, and we'll say we'll take this and we'll encode. Now you see here the two variants that it has. A is 1, where basically H is 8, or A is 0, where H would be 7, right? So both are good candidates. Well, we see here numbers, all kinds of numbers encoded, but none of them that really would help us look at a coordinate. Actually, if we look at these 3, 6, 10, 15, 15 is a pretty good number for a coordinate, but it starts here with a 4. And if you look at our coordinate system, it starts with a 3, so it's actually too big. However, if we do A is 0 and we say encrypt, we now see different numbers, and we still see a 15-digit number, but now it starts with a 3. That is a lot more promising, since we 15 number starts with a 3. That is the same here. Now, if you also note that it had to use the number sum up, we have here all the words. One of the key nice things of the decode is that you can put multiple things in there and it will decode them all individually. So sum all these up, so we can go to Wolfram Alpha, put them in here, and we'll get our solution that we're looking for. We just have to add these numbers together and we'll have our coordinates. So very plain step conversion if you knew what to do, right? It often is that way with puzzles. Now, just a little bit, as I mentioned, I often use my own tools. So let's say that we took the same sentence. I also have a base conversion tool that I worked on. And so same, we have the two alphabets, the from and the to alphabet, where we could say, okay, well, our from is the letters of the alphabet. We want to use a base 26 conversion. And now it will show it in all the different bases. It will show what this would look like, right? So we have all the different variants, including the base 10, which is the one that we're looking for. But of course, this one is pretty easy also if you want to do just base conversions. Say, okay, I have a certain number that I have here, or maybe several numbers. If the source, the input text is base 10, then it will show you what they would look like in another base, and you see individual numbers all the way till the base 36. Or if you say this one is not base 10, but maybe I think this one is, I don't know what base it is, but show me what's in base 10, you press the other button and it would show, well, if it was base 7, it would like this. If it was base 8, it would look like this. If it was base 9, it would look like this in base 10. So basically 2 conversions from conversions. But we've already solved the puzzle. I showed you 2 different ways of how to convert it. So yeah, another puzzle solved. So now we've reached the end of this video. So here are some of the websites that you can use. Geocaching toolbox that I talked about, the unit conversion, the Now Listen to Me, which I used in the puzzle, and of course some other ones that are very good tools to do conversions. It's always good to have multiple tools because, as I'd shown, some of them use a standard alphabet, some of them have a very custom alphabet, some of them are easy for base 26. So it's always good to have multiple tools for you available to do the tasks that you need to do. With that, I've reached the end of the presentation. I appreciate it if you would like or subscribe. That way you can support these videos and make sure that others will find the videos as well. If you have feedback, please leave a comment. Love to hear from you. Also, if you want to contact me, you can reach me at waterfan5 on the geocaching.com website, or you can email me at geocacher.waterfan5@gmail.com. Thank you very much for your time and hope you enjoyed it. Thank you. Bye.